Hello everyone, my name is Suptasish Sarkar, Assistant Professor in Mollohome Institute of Technology in Electrical Department. Today I will discuss a topic which is Maxwell equations in electromagnetic field. These are the contents. There is definition of Maxwell equation, Maxwell first, second, third and fourth equations. So what is Maxwell equation? Actually Maxwell's explains the electromagnetic wave physical significance and interpretation. Maxwell equations are a set of four equations that describes the behavior of electric and magnetic fields and how they relate to each other. Basically Maxwell takes two equations from electrostatic and two equations from magnetostatics. Maxwell equation has two forms. That's one is point form or differential form and another one is integration form. Maxwell first equation. It is taken from Gauss law of electrostatics. It states that a electric flux passing through any closed surface is equal to 1 by epsilon times the total charge enclosed by that surface. And we all know the total flux is equal to rho by epsilon. What is rho? Rho is the total charge enclosed in a volume. And also phi is equal to integration E dot ds. When we compare these two equations, we get rho is equal to surface integral d dot ds. And we know electric flux density d is equal to epsilon E. So from this integration rho v dv is equal to surface integral d dot ds. This is the equation of Maxwell first equation in integral form, and this rho v is volume charge density. Now come to the point form of Maxwell first equation. We know from previous slide surface integral d dot ds is equal to in volume integral d del dot d dv. So Maxwell equations d del dot E is equal to rho by epsilon is described mathematically and how electric field lines flow away from positive charge and towards negative charge. So here we can also say divergence of electric field, that is del dot D is equal to rho v. We know D is equal to epsilon naught E. So this is the point form of Maxwell first equation. Now come to second equation. This is taken from Gauss law of magnetostatics. It states that the net magnetic flux through any closed surface is equal to 0. That means there is no monopole does not exist. That is integration surface integral b dot ds is equal to 0. This is the integral form of Maxwell second equation. And then if we apply divergence theorem in this equation b dot ds, here we get in surface integral b dot ds is equal to 0 by epsilon naught d. So this is the integral form of Maxwell second equation. volume integral del dot b dv. As we know from the Gauss law of magnetostatic, surface integral b dot ds is equal to 0. So as well as volume integral del dot b dv is equal to 0. So this is the point form of Maxwell second equation. Now come to third equation. It is derived from Faraday's law of electromagnetic induction. So as we all know, the Faraday's law states that if a conductor present in a vicinity of a magnetic field, there is a EMF produced in it. So we all know V EMF is equal to minus n d phi by dt. N is nothing but number of turns. For simplicity, where we take n is equal to 1, so E is equal to minus d phi by dt. And previously we know phi is equal to integration b dot ds, and EMF is equal to line integral E dot dl. Now put 2 and 3 in equation 1, so we get line integral E dot dl is equal to minus d by dt integration b dot ds. This is the Maxwell third equation in integral form. For point form, we use Stokes theorem because it converts line integral to surface integral. By applying Stokes theorem, integration E dot dl is equal to integration surface integral del cross E ds. So from this and comparing line integral E dot dl is equal to minus d by dt integral b dot ds, and comparing by these two we get del cross E is equal to minus dB by dt. B is nothing but the flux density. This is the point form of Maxwell third equation. Now for Maxwell fourth equation, it is derived from Ampere circuit law, that is closed integral h dot dl is equal to I enclosed, and integration h dot dl is equal to, we can write surface integral j dot ds. This is Ampere circuit law for magnetostatics. By Maxwell, he added a displacement current here. When a conductor passing through a current, the electron flow, so for this current flow. This is for conduction, that is represented by J. So in Ampere's circuit law, there is no time variance as well as there is no displacement current. But Maxwell added these two, the displacement current as well as the time variance. So the final equation is closed integral h dot dl is equal to surface integral j dot ds and plus surface integral del d by del d ds. So integration h dot dl is equal to surface integral j plus del d by del d ds. This is the fourth equation of Maxwell equation in integral form. Now for point form, we apply Stokes theorems in the previous equation. So line integral h dot dl is equal to surface integral del cross h ds. So by this we can conclude del cross h is equal to j plus del d by del d, and we all know h is equal to mu 0 mu r b, and d is equal to epsilon naught E. So we can also write del cross B is equal to mu 0 J plus epsilon naught del E by del T. Here del cross B represent the del cross operator means to take the curl. Mu 0 is magnetic permeability in free space and del T is the rate of change of magnetic electric field del E by del T. And epsilon naught is electric permittivity of free space, J is electric current density vector, and B is induced magnetic flux density vector. So this is the point form of Maxwell fourth equation. So by this four equation, Maxwell explained how the electric charges and electric current produce magnetic and electric fields. Maxwell equations describes how the electric field can create a magnetic field or vice versa. This is all about the Maxwell equations. Thank you.